Welcome to this lecture number 9 on this NPTEL course in fluid mechanics for chemical engineering undergraduate students. In the last lecture, we started discussing a new topic, and the topic relates to description of motion in fluids. Okay. So, this topic is called fluid kinematics or flow kinematics. Flow kinematics. As I told you in the last lecture, in any branch of mechanics, there are two aspects to it. One is dynamics and the other is kinematics. Kinematics refers to description of motion without reference to the forces that cause the motion. To forces, and dynamics is the next branch, which we will come to a little later, where we worry about the forces and the motion that are caused by applied forces, okay, that are caused by the forces. Okay. So, the first job in any mechanical subject is to understand how to describe flow. पहले से So, in this topic we are going to discuss kinematics, and we are going to just describe flows, how to describe motion in fluids. So, in this context we introduced the notion of what is called a fluid particle. Okay. It is useful in the continuum hypothesis to identify what are called fluid particles. Okay. These are not real particles as in as in the case of a molecule of a fluid, but they are idealized hypothetical objects which are useful in describing flows. What are these fluid particles? Well, imagine you have a fluid, a container of fluid, and at time t equals 0 there is no motion in this fluid, the fluid is static, and let us say you can mark various points in the fluid using various colored dyes. Okay. So, I am just let me draw it slightly bigger so that it is more clearer. So, you can mark various points in the fluid using various colored dye, okay, and this is at time t equal to 0. So, in principle you can do this for continuously for all points in a fluid, because a fluid is a continuous medium within the continuum hypothesis, but for the sake of illustration I am showing a few points. So, what these points will do upon this is at time t equal to 0, I am using closed circles, okay, and at a later time upon application of force, this some kind of force, we need not worry at this point what causes the motion, there is some kind of force that causes a motion. At a later time t, all these points would move to some other positions, okay, in general. Okay. So, I am using open circles to denote these location of these points at a later time. So, this point for example can move here, this point could have moved here, this point could have moved here, this point could have moved here, and this point could have moved here. Okay. So, we are assuming that the dye molecules are not diffusing or the diffusivity of the dye molecules are so small that for our time scales of interest it is immaterial that the dye is diffusing. So, the dye faithfully represents a point in a fluid, okay, to the extent that you can resolve a point by the help of a dye molecule with the help of a dye drop, okay, and this dye drop which you are using to identify a point will in general evolve in time upon application of forces, because the fluid is moving. Okay. So, this is roughly a realization of this mathematical or abstract idea of a fluid particle. So, in principle you can identify at time t equals 0, okay, the position of various particles. Okay. So, with respect to a coordinate system, as usual whenever you analyze any problem in flow or fluids, you have to put a coordinate system. With respect to a coordinate system, you can label various points, okay, at time t equal to 0. How do you label points? Instead of using a dye molecule as I argued in this thought experiment, we can label each points by their initial locations. Okay. The idea is you are identifying each particle, fluid particle, on the basis of their initial locations with respect to a coordinate system, and at a later time what will happen is that these initial locations, the points that are identified by their initial locations, will in general evolve to a current location. So, schematically I will take one point, okay, and then at a later time this will be like this. So, the trajectory of this particle at time t equal to 0 is here, and then at time t is here. So, this particle may move like this, okay, and at a later time all these. So, this is the position at time t equal to 0 is denoted as x p 0, okay, and this is the position of a fluid particle at time t. Okay. So, the position at time t will of course of a particle will be a function of where it was at time t equal to 0. Okay. This is called, and of course time, because this is, you have to follow this particle, and at any time the location that this fluid particle occupies at a time t will be a function of time itself as well as where it was at time t equal to 0. Okay. This is called a particle path or a particle trajectory. Okay. Okay. Now, what is the use of having such an information? Suppose you were to experimentally measure such an information, and you can do it for not just one point as I have shown here, but you can do it for many points. So, another point will in general move like this. So, it can, so this point is at a slightly different initial position, and a later time of course it will occupy a different position, but in general the idea is you can label all points based on the initial positions, and you can follow their motion and represent it mathematically in this form. Usually this functional form is written as x p at time t is a function of x p 0 and time. So, instead of writing a function like this, okay, you use the variable itself as a function. So, this is a concise notation. So, once I have this information, I can find what is the velocity of a particle, okay, which was at time t equal to 0 at x p 0 at a later time t. This is the velocity of a fluid particle which was at time t equal to 0 at x p 0. Okay. Velocity from the fundamental definition in mechanics is the rate of change of position. So, we will have to simply take the position, the particle trajectory which is given by this functional form, okay, take the particle trajectory and differentiate with respect to time by keeping the particle label constant. What you are keeping constant here is that you are following the same particle and then you are measuring its trajectory as well as you can find quantities like velocity. So, what is being kept constant in this time differentiation is very important. What is being kept constant is that the initial position of this particle or the particle label is kept constant. In other words, okay, we are following the same fluid particle. That is the meaning of keeping x p naught constant. This description is called of fluid motion is called the Lagrangian, or sometimes it is called as material description. Okay. So, what this description means is that you are following properties of a fluid by following the position of each and every particle as the fluid is moving. So, the independent variables in the Lagrangian description are the initial position of the particles and time t. So, initial positions, these are the particle labels. Remember that the particles are labeled mathematically, but with the help of their initial positions, and this is time. So, for example, I need not just worry about purely kinematic quantities like velocity or position, but I can also say things like temperature as a function in the Lagrangian description. The temperature, okay, of in a fluid flow will be depicted as a function of the initial position of a fluid particle and time t. So, what it means physically is that suppose a particle was here at time t equal to 0, okay, and it is moving later on to time t to some other location. What this Lagrangian description of temperature means is that you are attaching a thermometer to the particle and you are moving along with the particle, and you are recording the temperature in the thermometer as you follow the particle. So, that is the meaning of keeping x p naught constant. You are attaching yourself or tagging yourself along with a fluid particle. For example, here we are interested in measuring temperature. So, we put a thermometer in our minds, okay, along with the fluid particle and measure the temperature of the fluid particle as you go along with the fluid particle. Okay. So, this is the Lagrangian description, okay, Lagrangian temperature field. Okay. So, what is the advantage of Lagrangian description? We have the motion, the current position of a particle as a function of its initial position and time. Once I have this is called the particle path or the particle trajectory or simply the motion of the particle. Now, I can calculate the velocity of the particle at a later time by taking the partial derivative of the particle trajectory by keeping x p naught constant, because x p is a function of x p naught and time. So, various points in the fluid will move differently to various other locations. So, if I want the velocity of this particle, I have to simply follow this particle at time t and then take its time derivative at time t. Okay. So, t is kept, this is the rate of change of particle is kept constant, rate of change of position with respect to time at a time t. Now, this is the velocity of a fluid particle. Now, acceleration in mechanics or kinematics is simply the rate of change of velocity that of a particle. So, that is also very simple, simply take the rate of change of velocity of a particle by keeping the particle identity to be the same, that is you are following the same particle and you are finding the rate of change of its velocity, that will give you the acceleration. Okay. Now, while this is very similar to what is normally done in Newtonian particle mechanics of point particles and objects, okay, this is not really suited ideally for fluid flow problems, because in a fluid, for example, if you are interested in flow in a pipe, okay, so this pipe will be in general connected to some reservoir, okay, it's figuratively shown like this. Okay. So, and so if you are interested in pressure drop across the pipe that is required to pump a specific flow rate, then you are not truly worried about various fluid particles, the identity of fluid particles that are entering and leaving, because all you are interested in is what is the force that is being experienced by this pipe, what is the drag force, and consequently what is the pressure drop. So, the Lagrangian description wherein we follow the same particle as a function of time is really not very useful, especially when you are considering fluid flow problems. So, instead of Lagrangian description, what is normally followed? So, the Lagrangian description, let me just write this, not suited for fluid flow problems. Okay. So, what is normally done in fluid mechanics is what is called the Eulerian description. Or spatial description of motion. Okay. So, what this means is the following. In the Eulerian description, we again put a coordinate system x, y, z, with respect to which we measure coordinates, laboratory coordinate system. Let us say the coordinate system is fixed in the lab. Now, here quantities such as temperature are measured as a function of the 3 fixed coordinates x, y, z and time. So, what we do here is that you take a thermometer and then keep the thermometer at a given point, and then move the thermometer to various points, okay, and then keep measuring the temperature. So, if you want the temperature at a given time, so you have to, if the temperature is changing as a function of both x, y, z as well as time, then what you have to do is you have to put many thermometers at various locations, okay, and each thermometer will locate will read will indicate the temperature at that location as a function of time. So, in the Eulerian description, okay, the independent variables are the spatial position of a point x, y, z and time. Okay. So, what is the fundamental difference between Lagrangian and Eulerian descriptions in a fluid flow problem, okay, in a fluid flow context? Suppose a fluid is flowing, okay, and in the Lagrangian description you will follow this material point or fluid particle, and then you will measure its temperature as a function of time. Okay. Suppose you are just worrying about a small time interval t and little later to t plus delta t. Okay. In the Lagrangian description, if you put a thermometer, this thermometer will measure, okay, the temperature of a fluid particle which was here at time t and which was here at a time t plus delta t. So, you are keeping x p naught constant and you are measuring temperature as a function of time. So, in the this is the Lagrangian. Okay. In the Eulerian description, in contrast, suppose you have well, let us just fix the location. Suppose you fix the location. So, this is a fixed location in space. At time t, let us say this location is occupied by a particle colored with blue, that is, this particle was residing at this point at time t. But at a later time, what is going to happen? So, this, let me just write that this is Eulerian. At a later time, what is going to happen is that at the same location, which is denoted by a star here, this point will not be the blue point will not be residing at the same location, because at a later time this blue point will in general move to, this is at time t, at time t plus delta t, but this location will be occupied by some other point at time t. Okay. So, the thermometer at a fixed location in space records, it does not record the history of temperature of a same fluid particle, rather it records the temperatures of various fluid particles that happen to be at a given location at various times. So, the sense of history of temperature history or velocity history, or that this historical information of a given fluid particle is lost. Historical information is lost because we are not following or tagging along with the same fluid particle. Instead, we are sitting at the same point and we are merely measuring the temperatures that various fluid particles are going to occupy that point at various times. Okay. But the Eulerian description, even though it has lost by its construction, it has lost the sense of history of information of a given fluid particle. Okay. But it is still very useful, because in laboratory it is easier to measure temperature easier to measure properties at fixed locations rather than follow fluid particles or material particles. Okay. So, in fluid flow problems there are two reasons why Eulerian description is preferred over Lagrangian description. Firstly, even if it were feasible, having the information about what are the various fluid particles that are occupying, let us say, a given section of pipe is really not relevant to many practical questions such as what is the pressure drop, because here we are not really worried about which fluid particle is coming and exerting a drag force, okay, or we are merely interested in the force that is experienced by walls of a pipe or a sphere that is moving or so on. Okay. So, the historical information is not of practical importance in general, okay, in practical applications, and also even if you want to measure such a historical information in the Lagrangian sense, it is not easy to measure in a lab, because you have to really follow the same fluid particle and it is not easy. Rather, it is easier to fix probes such as velocity probes or pressure probes or temperature probes at a given point in spatial location or at various fixed points in a spatial locations rather than moving along with a particle. So, in the Eulerian description, the independent variables are the fixed locations of various points in space and time. Okay. So, the Eulerian description is very easy to measure in laboratory. Okay. But so, if you are interested in kinematic quantities such as velocity of a fluid flow is described in the Eulerian description as a function of various points in space and time. Suppose you have a flow in a pipe, okay, and you put a coordinate system x, y, z. Okay. So, you can sit at this point and measure its velocity as a function of time, then change the location of observation, and then or you can put multiple probes for velocity and then measure the velocity at various locations, fixed locations in space as well as time. Okay. That is the main crux of Eulerian description. But there is a problem with Eulerian description in the sense that suppose I have this information, temperature as a function of spatial location and time, okay, and suppose I take this partial derivative, temperature is a function of x vector is a combination of 3 variables. So, x, y, z and time. So, when I say partial temperature by partial time, I am keeping the location x, y, z constant. I will figuratively denote this as vector x. So, suppose I have given the temperature field, let us say from an experiment. So, the temperature field is given as T x, y, z time, or in short form I will simply write this as T x t. Given this information, suppose if I calculate at a spatial location, okay, this is not telling me how the temperature is changing. So, this is a partial derivative. So, if this fluid particle is moving from time t to t plus delta t, okay, its temperature can in general change as you follow the particle. Okay. But this is not giving that information. What this derivative is giving you is that if you sit at a point, what is the rate of change of temperature that you will feel at that point, okay, locally. So, the sense of history is lost in the Eulerian description. While it is not critical in probably applications like temperature, suppose you are interested in kinematic quantities like acceleration. Okay. What is acceleration? In the Lagrangian description, if you recall, is basically the rate of change of its position by keeping the label of the particle constant. Okay. But in the Eulerian description, okay, v is written now not as a function of the initial positions, but rather the spatial locations in a coordinate system. So, first of all, I do not have this particle path information. Even if I have the velocity information in the Eulerian sense, I cannot calculate acceleration as partial v partial t, because now I am not following the same particle, I am merely sitting at the same point in space. Whereas, in the Lagrangian description, acceleration of a particle is the rate of change of its velocity, because you are following the same particle. So, what is being kept constant is this. Okay. Okay. So, in the Lagrangian description, it is very clear what is acceleration, because you are merely keeping the initial location of the particle constant, you are following the same particles. But in the Eulerian description, if you have the velocity field like this, you cannot compute acceleration by simply taking the partial derivative, because this does not have the information as to how a given particle is moving. Okay. Given particle is moving as a function of time. This information is not there in the Eulerian description. So, we cannot compute accelerations from the Eulerian velocity fields. Okay. So, you may ask, why is this an issue? The reason why this is an issue is that when you want to eventually go to dynamics, you are going to apply the Newton's second law of motion to a continuous fluid. The Newton's second law of motion says that force on a particle, an identifiable piece of matter, is mass times acceleration. So, we need the acceleration, okay, when you want to eventually write down equations of motion for a flow. But we also want to work only with the Eulerian framework, because it is much simpler and it is more useful. Okay. But fundamentally we need accelerations. So, we need acceleration, but acceleration cannot be obtained from velocities like this. So, how do I connect the acceleration to the velocity field, Eulerian velocity field? Okay. That is, the question is, given the Eulerian velocity field v as a function of x t, okay, how do I compute accelerations? Okay. So, there is a very nice framework, okay, for doing this, and this is the reason why we introduce the Lagrangian description. Although we are not going to use the Lagrangian description, we do need the notion of a Lagrangian description in order to compute acceleration of a fluid particle. Okay. So, instead of doing this for acceleration, I am going to illustrate this for a derivative like temperature. That is, the question is, given the spatial description or Eulerian description of temperature, how do I compute partial t as I follow a particle? Okay. This is a Lagrangian time derivative. See, notice that the Lagrangian description and Eulerian description differ merely by what are the independent variables. This is the Lagrangian description, this is the Eulerian description. Okay. So, they change not only by the independent variables that we choose to describe the problem with. Okay. So, I am going to now do this thing called substantial or material derivative. This will help us to calculate the time derivative as we follow a particle from an Eulerian description. Okay. So, to motivate this, I will take a very simple context. So, imagine you have a channel in which fluid is flowing with constant uniform velocity. The velocity is constant in the sense that, suppose you call this x and y, okay, the velocity is constant in the y direction. Okay. It is not realistic, but this is just for the sake of our illustration. So, we do not worry about this part, that why the velocity is uniform. Let us assume that the velocity is largely uniform. Okay. Now, let us imagine, okay, that there is a location. So, let me introduce a location. This is x equal to 0, okay, and here a fluid particle. Let us focus on two fluid particles, blue and red. Okay. So, here there is a red fluid particle at time, okay, t equal to t 0. Let us say we are at time t equal to t 0, okay. And then we have another fluid particle which is blue in color at the location x is minus v naught delta t. Since the fluid is flowing at a constant velocity, okay, and okay. So, we are looking at two fluid particles which are separated by a distance delta x, and that delta x is v naught delta t, where delta t is the time interval that we are going to introduce just shortly. Okay. So, imagine two fluid particles identified by their colors blue and red, and we are following the motion of these two fluid particles as a function of time. Okay. So, this is at time t equal to t 0, this is the situation. The red particle is situated, the red particle is situated at x equal to 0, and the blue particle is situated slightly behind, and since its x is positive in this direction. So, this is at a distance minus delta x, and since delta x is v 0 delta t, x is 0 minus v 0 delta t. So, this is minus v 0 delta t, this is slightly behind the red particle. Okay. Now, at a later time, imagine after a time t naught plus delta t, what would happen? Okay. Let us try to draw, this is x equal to 0, okay. This is x equal to v 0 delta t. Since the fluid is moving, this particle will move eventually. So, the red particle will move from 0 to v 0 delta t, and the blue particle will move from minus v 0 delta t to x equal to 0. Okay. This is the status at time t equal to t 0 plus delta t. Okay. So, let us mark also at this point the Lagrangian labels of these particles. Okay. The Lagrangian labels of these particles is their initial position at time t equal to 0. So, the red particle is denoted by x equal to 0, that is the position of the particle at time t equal to t naught, and the blue particle is denoted by x equal to minus v 0 delta t. Okay. So, the Lagrangian, so x naught, I mean since the Lagrangian variables are denoted with that. So, this is the position at time t equal to t 0. Okay. So, this particle, while it is present, this is also x naught is minus, okay, x naught is minus v 0, and x here the red particle x naught is 0. Now, even at a later time t 0 plus delta t, this blue particle is still denoted by the same Lagrangian label, because the Lagrangian description uses the position of the particles at an initial time, let us say t naught, to label them. So, x naught is still minus v 0 delta t, and x naught for this red particle is still is 0. So, this is the initial position of a particle which is currently at x equal to 0. This is the initial position of this red particle which is currently at x equal to v 0 delta t. Okay. So, these are the Lagrangian coordinates, these are the Lagrangian labels or coordinates. Okay. Now, let us say we are having we are measuring temperature at this point, we are measuring temperature at this point x, okay, x equal to 0. Okay. So, we are measuring temperature by putting a thermometer, okay, at x equal to 0. Okay. And so, here as well. So, we are placing the thermometer at x equal to 0, this is a thermometer. Okay. What this thermometer is measuring as a function of time, at time t equal to t 0 it will measure the temperature of the red particle, while at time t equal to t 0 plus delta t it will measure the temperature of the blue particle. This is the key to our derivation. Okay. So, it is very simple, because the thermometer is fixed at the same spatial location x equal to 0, which I am denoting by this green color, but the points that are occupying the same spatial location are different, the material points that are occupying, the fluid particles are different, because the fluid is continuously flowing. Okay. So, let us understand what we will do by calculating at the partial derivative of temperature with respect to time at x equal to 0 at the same location. What is this? This is from fundamental definition of calculus. This is T 0 plus delta t minus x equal to 0, t equals T 0 divided by delta t in the limit as delta t goes to 0. This is the fundamental definition of a partial derivative, and since it is a constant, we are keeping x is constant at 0. So, this label should be, this is a function of two variables, t is a function of x and t, this is Eulerian description. Since x is kept constant at 0, we simply have to take the derivative with respect to time. Now, let us try to understand what this means. Okay. At x equal to 0, at time t equal to T 0 plus delta t, let us look at picture. Okay, this is time T 0 plus delta t. At x equal to 0, the particle that is occupied is the blue particle. So, the temperature the thermometer will measure is nothing but limit delta t tends to 0, okay, temperature of the blue particle, which is identified by its Lagrangian variable. So, which is x naught is minus v naught delta t and time is T 0 plus delta t minus, here the temperature at x equal to 0 at time t equal to 0 is namely that of the red particle, because at x equal to 0 at time t equal to 0, notice that it is the red particle that is occupying, and the thermometer will measure at time t equal to delta t T 0 the temperature of the red particle, and the red particle is identified by its Lagrangian variable, which is nothing but t x naught is 0 at time t 0, okay, divided by delta t. So, essentially we are trying to measure the temperature at a given spatial location in this illustration. So, we are putting a thermometer at the position x equal to 0, the same position, same spatial location with respect to this coordinate system, and but at x equal to 0 at time t is equal to T 0, the red particle is occupying the location, spatial location x equal to 0. At a later time, the same spatial location x equal to 0 is occupied by the blue particle. Okay. So, when you take this measurement and when you take the partial derivative of the temperature using this measurement, okay, partial derivative of temperature with respect to time is nothing but okay, the partial derivative of temperature is limit time at that spatial location x equal to 0 is temperature at a later time minus temperature at T 0 divided by delta t as delta t goes to 0. Okay. But the key realization that we must have is that the temperature at x equal to 0 at a later time corresponds to that particle which was there at a later time, which is namely the blue particle. Now, the blue particle is denoted by its Lagrangian label x naught is minus v 0 delta t. Now, the temperature at x equal to 0 at time t 0 is due to that of the red particle. So, we can change from x equal to 0 to x naught equal to 0, because the red particle is identified by its Lagrangian variable, which is merely x naught equal to 0. Okay. So, this is the key realization when going from Eulerian to Lagrangian, that okay. Okay. So, that we can change the labels from Eulerian to Lagrangian by knowing which particle was occupying the current position and the previous position and so on. Okay. So, having done this, we will just do a simple, we are still having on the left side the spatial derivative, the Eulerian time derivative of the temperature field. Okay. So, I am going to do a small mathematical simplification by adding and subtracting. So, let me write the first two terms, x 0 is minus v 0 delta t, time is T 0 plus delta t. Let me subtract time temperature at x 0 is minus v 0 delta t and t is T 0, and add the same thing again, x 0 is minus v 0 delta t, t is T 0 minus t x 0 is 0 and then T 0, and then divided by delta t. So, let me put a 1 over delta t here, that is of course stays. Okay. Now, here we are keeping x 0 the same. Okay. So, what is this term? So, let me mark this with a red, so that you can see what is this term. This term is nothing but the red term that is here is nothing but. Okay. So, let me write this down separately. The red term is nothing but, write in red color, so that it is clear. T at x naught is minus v 0 delta t at time t 0 plus delta t, minus t at x naught is minus v 0 delta t at t 0, okay, divided by delta t, that is of course there here common, and limit delta t going to 0 is nothing but, see here we are keeping x naught constant. Okay. Okay. So, this is nothing but the time derivative as you keep x naught constant. Okay. So, this is the time derivative as we keep x naught constant. Okay. This is the Lagrangian time derivative. This is the time derivative as you follow the same particle. Okay. Here originally we are measuring the time temperature at the same location, but here this part of this expression corresponds to the rate of change of temperature with time as you follow the same particle, because the particle is being fixed here. Okay. So, this is what we are after. We want to calculate the rate of change of temperature with time as you follow the same particle. Okay. But there is one more piece here which we will have to tackle. So, what is that piece? Let me write it in blue color. So, we still have this additional piece, limit delta t tending to 0, 1 over delta t, t at x naught is minus v naught delta t, t equals t 0, minus t at x naught is 0 at the same time, okay, divided by delta t. Now, suppose you consider the change in position delta x. Delta x is nothing but v 0 delta t. Okay. Recall that this point, the 2 points x, the 2 points are separated by a distance delta x, x equal to 0, and this earlier distance which is nothing but minus v naught delta t. Okay. That, so, delta x, the separating distance is v 0 delta t. Okay. So, this is nothing but, we can write this as, so 1 over delta t t x naught is minus delta x t 0 minus t x naught is 0. Okay. Now, if you look at what is partial derivative of partial t partial x at x equal to 0, you can write this as t at x is 0. Okay. But we can also, okay, before I do that, we can also change the labels now. Okay. When x naught is 0, okay, x is also 0. Okay. This is nothing but, okay, so let us go back to the figure in the previous slide. When x naught is 0, x is 0. When x naught is minus v 0 delta t, x is also minus v 0 delta t. So, we can change this to the Eulerian description as limit delta t going to 0, 1 over delta t. When x naught is minus v 0 delta t, x is also minus v 0 delta t, t 0, minus t, when x naught is 0, x is also 0 at t 0. Okay. This is what we have. Okay. But if you recall, what is the fundamental definition of the rate of change of temperature with respect to position at a given time? Let us say this is t at x equal to 0 minus t at x equal to 0 minus delta x divided by delta x. Okay. But in our case, delta x is nothing but v 0 delta t, Okay. So, I can write this as, so instead of delta x I can write V 0 delta t here. Okay. So, t at x equal to 0 minus t at minus delta x divided by V 0 delta t. This is partial t partial x at constant time. Okay. So, I can pull this V 0 up here, okay, and realize that what I have here in this expression is nothing but, okay, I have here t at x equal to minus delta x t 0 minus t at 0. Okay. This is nothing but minus partial t by partial x times V 0 delta t. Okay. So, if I go back to my original expression where I have two terms, okay, if you remember, let us go back to this expression. I have two terms. So, let me just simplify here itself, partial t partial of temperature with respect to time at x equal to 0. So, this term we simplified as, so we have still 1 over delta t, limit delta t going to 0. Okay. Well, we have taken the limiting process. So, let us remove the limit now. This is nothing but, you have the first term we already simplified it to partial t at x 0. The second term is now simplifying to minus V 0 delta t partial x. Okay. Now, what we are after is not, so let me just write down this result once again, partial t at constant x is nothing but partial t okay, at constant x 0 minus V 0 partial t partial x at constant time. Okay. So, what we are after is this term, because this is something that is easier to measure experimentally, whereas this is something that is difficult, because this is the rate of change of temperature as you follow a point, whereas this is the rate of change of temperature at a fixed point. So, finally, we have rate of change of temperature when you follow a particular fluid particle is equal to rate of change of temperature at a fixed point. This term will go to the other side. If you take the negative sign to the other side, it becomes positive, okay, at constant time. Okay. Sorry, this is x now, because this is in the other side, this is x. So, this is called the Lagrangian or substantial time derivative, or in fact sometimes it is called the material derivative. Okay. This is the usual partial derivative of time with respect to time, Okay. When I take partial derivative of temperature with respect to time, I have to keep the spatial location constant. So, this is the spatial location at a given point in space. Okay. We can call it x equal to 0 in this example, but in general it can be any x. Okay. Now, this one is what is called the convected rate of change. It is called the convected rate of change of temperature. Okay. So, here what this is telling is that a particle that was here, okay, will move from one location to another by virtue of flow, that is where this velocity is coming in, and the temperature difference is going to feel is given by the Eulerian spatial derivative of temperature. Okay. So, this is essentially the temperature difference between these 2 points, okay, as given by the Eulerian description, and if you multiply by the velocity of the particle, by the velocity at which the particle is moving, okay, then that is going to give us the convected rate of change. So, this is sometimes called the local rate of change. This is called the convected rate of change. Okay. So, in general, therefore, we can write, okay. So, this is the Eulerian derivative, this is the substantial derivative, so this is the normal partial derivative, sorry, this is the Lagrangian derivative, this is the normal partial derivative, and this is the convected rate of change. So, in general, the rate of change of any property like temperature as a function of time for a fixed Lagrangian particle, okay, is given by the rate of change of temperature with respect to a fixed point in space. Okay, let us still keep x as a single variable. I will generalize it to more 3 dimensions shortly, plus the velocity in the x direction times partial t partial x at a given time. So, this right side can be computed completely from an Eulerian description, whereas this is inherently a Lagrangian quantity, because you are following the same particle. Okay. Now, sometimes in textbooks you will find that instead of having the same symbol with respect to a different independent variable being kept constant, this is normally denoted by dt dt. So, the capital D is reserved for substantial derivative for a single, if the temperature is function of only a single coordinate x and time. So, it is the velocity in the x direction times partial t partial x constant time. Okay. Now, I can generalize this to more dimensions. Instead of just having one dimension, suppose the temperature is a function of not just x, x, y, z and time, then what is the substantial derivative? The substantial derivative is the time derivative of temperature as you follow a particle. Okay. So, what is it? So, we can generalize very straightforward, in a very straightforward way, is partial t at constant spatial location plus V x partial t partial x plus V y partial t partial y plus V z partial t partial z. Okay. So, again, so here partial t partial x is calculated by keeping y z t constant. This is calculated by keeping x z t constant. This is calculated by keeping y x and t constant. Okay. So, that is the basic idea of a substantial derivative, wherein by purely having a completely Eulerian information, we are able to calculate the rate of change of a quantity like temperature as you follow a particle infinitesimally at a later time delta t. Okay. Now, if you try to see whether we can write this in a slightly better form. Okay. Now, this is, okay, let us just look at this part of the equation. Okay. Let us just look at this part of the equation and see whether we can write this slightly in a more compact form. So, this is like if I have two vectors a and b, and each vector is given by a x in terms of its Cartesian coordinates. Okay. B is similarly given as b x I plus b y j plus b z k. Then a dot b is nothing but a x b x plus a y b y plus a z b z. Okay. Likewise, if you look at this expression, it looks like a dot product of two vectors. One vector is the velocity, the other vector is the gradient of temperature. Okay. Let me just explain how this comes about. So, if you look at velocity, this v x I plus v y j plus v z k. Okay. You look at gradient of temperature, it is nothing but partial t partial x I plus partial t partial y j plus partial t partial z k. If I take the two dot products, the two dot product of these two vectors v dot del t, then you get v x partial t partial x plus v y partial t partial y plus v z partial t partial z. So, we can write the substantial derivative of temperature in a more compact form as the local time derivative of temperature at a fixed spatial location plus v dot grad t. This is for 3 dimensions. Okay. this is the local rate of change, sometimes this is called the local rate of change, okay, and this is called the convected rate of change. Okay. So, this is a very important concept in fluid mechanics, because this is a vehicle that allows us to calculate the substantial derivative idea is a vehicle that allows us to calculate the rate of change of many quantities as you follow a fluid particle, okay, from a given time to a later time, purely based on Eulerian description, quantities based on Eulerian description. So, we will stop here and we will see you in the next lecture, where we will continue further in fluid kinematics. Thank you.